Hello again. Welcome to part 3 of my 3-part mathematical challenge series. In part 1 I explained that the challenge is to agree with me or not on whether or not it's a good idea to get rid of infinity from mathematics. Dispense with it altogether. In part 2 I challenged those of you that think it's a good idea to figure out how to change the foundations of mathematics so that we can put the mathematics of finite numbers on a rigorous foundation. And now in part 3 I'm going to challenge you to figure out how to redefine concepts like limits and continuity that depend on infinity for their definition in orthodox mathematics. Redefine them in such a way that we can still prove all the same theorems in calculus that are important in doing computations that we do for all kinds of purposes. I believe that all the same theorems can be proved so that we can use mathematics the same way we always have in doing calculations, except that at basis the mathematics is going to be grainy, because we only have a finite set of numbers that we deal with. And that's the case in actual computation anyway. No one has ever done a calculation using an infinite number. All numbers we use are finite. They're finite approximations of numbers that are claimed to be infinite, but they're not. Or numbers that may have an infinite number of digits and so on. Incidentally, in this mathematics, we lose a lot of familiar things that people are going to sorely miss. But as I pointed out, that mathematics is still available, and if you like those kind of things, you can still use the old mathematics. The new mathematics will just be different. We'll lose things like irrational numbers. All the numbers are going to be rational in the practical number system. We're also going to lose infinite series. In practical numbers, all series will be finite. So the number system that I propose is what I've called practical numbers, and they are determined by the acceptance of a largest integer, which I've called m for the purpose of these videos. And so the only numbers we have to deal with, the only integers we have to deal with, are those from minus m to plus m. And the only smaller numbers we have are quotients of integers that are within that range. Not all quotients will be defined because, well, maybe all quotients will be defined within that range. But at any rate, I already went through in the second video the limitations on what operations are defined. And we are limited. So, as I said, infinite series are not allowed, so we'll only have finite series. And we also need to come up with a new definition for limits and continuity in order to develop calculus with practical numbers. The way continuity is defined in orthodox mathematics is that there are two numbers, epsilon and delta, involved, and the definition says that as long as you keep the independent variable within the range of delta around a certain point, then the function won't vary by more than epsilon within that range. And the idea is that the number epsilon is chosen first, and then the number delta is calculated and produced afterwards to restrict the function suitably. Well, that depends on the fact that no matter what number you pick as epsilon, I can always pick a smaller number, delta, within that. In other words, there's no smallest interval. If you pick a number epsilon, I can pick a number epsilon over 2 that's smaller. In practical numbers, that won't work. because there is a largest integer, which automatically means there's a smallest non-zero interval or non-zero number, and that's 1 over m. There are no smaller non-zero numbers than 1 over m, and so this epsilon delta method doesn't work because we get down to this what amounts to a pixel size or grain size in our mathematics, and we can't wiggle any smaller than that. So here's what I propose in general. I mean, I don't have this worked out, but in general, here's kind of the way I propose we deal with that problem. In our practical number system, we have the maximum integer, which I've called m, and the numbers from minus m to m are defined, and so we call those defined numbers or just numbers. But then within that range, we can restrict ourselves further, and in video number 2 I went through the restrictions that come from the definitions of addition, multiplication, and subtraction. I didn't put division in here, but those limitations say that we have to stay within this hyperbola set. And if you notice that on this hyperbola there's the point or the pair square root of m, square root of m, and if we multiply those two numbers, square root of m times square root of m, we get m, which means this number is okay, it's practical. So if we restrict ourselves to this square that's 2 square root of m on a side around the origin, then we can multiply and add and subtract any numbers in that range, in that box. We still can't divide those that have a divisor of 0, but that's not much different than in orthodox mathematics. So now let's call these the practical numbers. So the practical numbers are those that are that have an absolute value less than the square root of m. What I propose is that we think of this intuitively in terms of a computer screen with a pixel size. And so we can talk about continuity as long as the pixels are contiguous in any function plot. So the pixel size will be 1 over the square root of m, because the square root of m is a practical number. That is, we can multiply any number smaller than square root of m and get a number that's defined, that is less than m. So if we have a pixel size that's 1 over square root of m, then we can choose, and we consider that to be epsilon in the traditional definition, then that will allow us to choose numbers as small as 1 over m, which are smaller yet, as our delta, so that we can define an interval delta around the point in question down to as small as 1 over m, and show that the function is restricted to 1 pixel size, which would be 1 over the square root of m in invariance. Now that's just a sketch of how I would do it. We would need a suitable definition for limits, and again it would involve an interplay of 1 over m and 1 over square root of m, I believe. But I think that intuitively you can see that we could define continuity to be such that if you plotted on a screen with a pixel size of 1 over m, the function will be continuous if and only if the variance is within 1 pixel size. And for all practical purposes, that's sufficient. If it's not, we just simply get a screen with a higher resolution with smaller pixels. So that's just a brief sketch of how I would approach redefining limits, continuity, and convergence so that we could begin proving the theorems of calculus, which I believe can be done, and I believe we'll get the same results, and thus we'd have the same powerful mathematics we have today, except that it would be grainy and probably more suitable for describing our grainy world. So those are the components of my challenge. Please pick up the challenge. If you disagree with the whole approach, let me know in the comments. If you think the approach has merit, give some thought to developing the foundations or developing the calculus and analysis using practical numbers so that we can get a mathematics that might work better in our world. So I thank you for watching. Please send your comments, and good luck.